Good afternoon, everyone. My name is Bowie, and I'm the Technical and R&D Laboratory Manager at Geofabrics for the GREE Laboratory. Today, our webinar will talk about the testing geosynthetic materials and their interactions with the surrounding environments. We will basically focusing on the following 6 parts in today's webinar. First, we want to talk about the importance of doing testing. Then we will give a virtual tour in our GREE Research and Development Laboratory. And then we will talk about the GAI-LAP accreditation, which the GREE Lab has, and what does that mean. Then we will dive into the testing area, and I divide that into 2 parts. First is the basic index geosynthetic test, and then it's about the performance and specialized tests, which I find the most interesting part of this presentation. And finally, we will spend a couple of minutes just to go through the research and development capability of the GREE laboratory and some site trial we are currently doing, which you might find interesting as well. So let's start from the reason we are doing testing here. So in a good design, safe is important, but also people want a cost-effective on the material construction and the maintenance. And that requires us to have a clear idea of how the design facility or structure to perform at the conditions it will face during its service life. To have that, we must have the confidence on the material, which eventually give us the confidence on the design. This includes but not limits the soils, aggregates, concretes, and in our case, the geosynthetic materials used. And this is like a fine balance we want to achieve between the safety and the cost. And by doing some testing, you would know your material well and help you to achieve that balance, I believe. And the geosynthetic products do have their very unique behaviors under various working conditions. And these could determined by their raw material, how they are manufactured, the conditions of the service, and the, for example, like the load, the chemical conditions, temperature, and the moisture. And I must emphasize, it is really unsafe to assume that different geosynthetic products will behave identically, or to assume that same geosynthetic product behaves consistently when they are exposed to different environments. And apart from that, the testing also helps us to gain the quality control and help us know the basic characteristics of the material, understand how they react to the surrounding environment. A quick example here is our bentonite chemical compatibility when exposed to different chemical environment, and help us to estimate their durability. For example, we can do those 100-year service life estimation or assessment on the geotextile or the geomembranes we use. And also it helps us to validate the performance for the new geosynthetic products that has been developed. Essentially, it's like know your product, understand why they perform in this way, and help us to predict how they are going to perform on the site. The next one, we will have a quick tour in the GREE Research and Development Laboratory. So what the GREE stands for? The GREE stands for the Geosynthetic Research, Innovation and Development. And the GREE Laboratory is a specialized research and development oriented facility here at the Geofabrics. Lab works not only within the Geofabrics, but also with the external clients to develop and validate the right geosynthetic solutions with the consideration of very specific project conditions. We are located at Gold Coast, Queensland, and we are proud to say that we're equipped with very state-of-the-art testing equipment in the geosynthetic and geoenvironmental test disciplines. And those test methods we do here include, but really not limited to, the following Australian standards, ASTM methods, BSE, and ISO methods, and many in-house test methods as well. And we are also proud to say we have a lot of collaborations with the industry and academic leaders in the cutting-edge geosynthetic research and development field. Just to name off a few, our main equipment in the lab here includes 17 triaxial permeability testing cells, and all of them are with the toxic environmental chambers. And we have 3 geotextile cushion protection efficiency testing cells. We have 2 universal tensile testing machines, one for testing the fibers only, and the other one testing the geosynthetic materials. And we have 4 laboratory ovens, and they are quite useful to carry out hot leachate immersion tests to assess the durability or longevity of the geotextiles or the geomembranes. And we have a 300 millimeter large-scale shear box with a special designed geosynthetic interface and internal shear test module. And we have 1 in-plane transmissivity flow testing equipment for the geosynthetic drainage materials, such as the geocomposites and the geonets. And we have many other equipments as well, just not listed here in detail. And also, the GRAI laboratory is actually GAI-LAP accredited. So what is GAI-LAP accreditation? GAI-LAP stands for the Geosynthetic Accreditation Institute Laboratory Accreditation Program. So it is a program to ensure that the accredited lab is capable of properly rendering the tests they perform. GAI-LAP essentially frames around the ISO 9000, ISO 17025, and ISO 17011, but it is tailored to the needs of the geosynthetic testing community. So what does mean being GAI-LAP accredited? So we need to participate the yearly GAI-LAP proficiency testing program with another more than 100 labs and compare the testing results together. That help us to keep the lab properly equipped and prepared to do the test properly. And on the right-hand side here is a general GAI-LAP flowchart for the accreditation program. And for the details, you are welcome to visit the Geosynthetic Institute website shown here. And also, you can find the test methodologies we are accredited for in the GRAI R&D lab in the link below here. So currently, we have more than 40 ASTM test methods accredited and more than 10 ISO test methods accredited in the GAI-LAP program. Next one, we will dive into the basic index geosynthetic test. You might ask, why do you separate the tests into the 2 categories? The basic index tests are the ones you often see in a specification. For example, the one I screenshot here from the GRI GCL3 standard specification. And most of the test methods listed here, they are actually the basic index tests. So these tests are often done in the manufacturer MQA lab for the quality control purpose and also by a third-party laboratory to carry out the IQA tests when delivered to the site. And similar tables often seen in other GRI specifications. Just to take a few examples like geotextiles, geonets, and geomembranes. And you may also find those test methods in those design specifications from the designers. And among these tests, most often requested down here at the grade are those short-term mechanical property tests. These properties are important because in the application where those geosynthetic materials are required to perform a structural role or to survive the installation damages or localize the stress, it's important for them to remain certain mechanical properties. The following fews we will quickly go through, including the tensile strength, the joining strength, pure strength, puncture resistance, and compressive strength. Let's first talk about the tensile strength. Note that for different type of the geotextile or the geosynthetic material, ASTM do have different or specifically designed test method for them. For example, you could say the GCL, geonet, geotextile, geomembrane, or the geogray. They actually share very different test methodologies, which request a different type of different size of the specimen or the loading rates to be carried out during the test. In the tensile strength test, certain parameters or key parameters are determined in those tests, include the tensile strength and the elongation of the material, either at the max tensile strength or at the break. And in some cases, the modulus are determined as well. And you might have already discovered that we have actually 2 test methodologies for the geotextile tensile strength. And simple answer is like there is no simple correlation between the two test methods since they are using different specimen size and different loading rate as well. And all these parameters may account into the differences of the results you obtain from the two methods here. The next strength that's often requested for is the joining strength. Because remember, on the side, our panels of geosynthetics are often joined to the other one next to it by different methodologies, such as sewing or thermal fusion methods. And those joining strengths is kind of crucial to ensure the good connections and the seams remain when the joint panels experience tear or shear force during the construction in the service lives. An example here is the ASTM D6392, which tested the shear and TPO strengths of the joint geomembranes. And for the geotextile seams, because we have different ways of doing the seams, such as the sewn, the thermal bonded, and using the adhesive, they actually use different size or shapes of the samples to carry out the test. So it's really important to make sure that the correct sample shape or correct type of the test are being requested in the lab and carried out at the same time. The next one is called the peel strength. So this is mechanical properties that's important for certain composite materials, such as the GCLs or the geocomposites, as they are made of different layers joining together. And the peel strengths between those layers, or sometimes the so-called applied adhesion or the bonding strengths, can be quite important, particularly when they are used on the slope. Example here is D6496, which is a test method for testing the applied adhesion or the bonding strength of the geotextiles in the GCLs. And on the right-hand side, this is testing photos of us testing geocomposite drain materials applied adhesions using the ASTM test method D705. And when the barrier or the geotextiles are used on the site, one of the mechanical properties designers also very value is the puncture resistance. This resistance is important for geosynthetic materials such as the GCLs, geomembranes, and sometimes geotextiles. And in STM, we actually have two different test methods, just focusing on the puncture resistance here. First is the CBR puncture, and then the second one is the index puncture. They actually use very different test methods, including the specimen size and the puncture row dimensions. So taking an example here, the ASTM D4833, which tests the index puncture resistance, which is usually done for the geomembrane materials. You can see the puncture, the puncturing rod is actually with a very small diameter, about 8 millimeter here. While when it comes to the CBR puncture for the geotextiles and the geosynthetic related products, it becomes a much larger plunger with a diameter about 50 millimeter. So naturally, we often received those questions, say, if you have a direct correlation between the two methods, because we happen to ask the wrong test methods on the specimen we want to test. The simple answer is, well, some of the studies did have a go on the comparison between the results getting from the two test methods on woven and non-woven geotextile. And here are the results. While I would say there do seems to be like a linear correlation shape between the CBR puncture and the pin puncture strengths, I wouldn't be so confident to actually interpret a single or individual product values using one of the values obtained here to get another value. Therefore, for us, we really believe it's important to clearly specify which method to be used, and that same method will be actually tested in the lab to obtain the correct values. The final mechanical properties we want to go through is the compressive strength, particularly the short-term compressive strength. So this is particularly important for some geosynthetic drain products like the GeoNet and the geocomposites, because as they are being compressed, their drainage capacity can be affected by the normal stress they are going to withstand. And the short-term compressive strength is therefore a parameter that can indicate how these materials respond to the normal stress. And generally, we have two different methods to investigate such behaviors, including the D1621 and the D6364. Notably, the two methods here are different from each other, including the specimen size, the way of interpreting the testing curves, as well as picking up the yield point here. But I do want to spend an extra minute just to discuss about the ASTM testing method D6364 here. The reason I want to spend the time on this test method is when tested as per this method, note that not all the geonets or the geocomposites, they have a notable yield point, particularly for a triplanar geonet, and then brings the question, when or where do we select the point to name that as a compressive strength? Well, in this case, we can have a look on these typical curves down on a triplanar geonet. As you could see, there is no notable peak or yield point, or you could say like multiple yield points here. So which point we should actually go to select as a compressive strength? We can actually analyze why we have such 5 different stages here per se. Stage 1 is actually the toe correction when the product starting to take force. And step 2 is the change of the structure of the outer ribs in a triplanar geonet when they're entering the yield condition. Step 3 is the time when the central rib in the geonet starts to really take the compressive force. And the point 4 is where that center rib start to enter into the yield point. And step 5 is like the material starting to lose its three-dimensional structure. And we are just looking at the compressive properties of the PE. Hence, here you have a very steep, slope. And we at the grid suggest that it's possible the best way to select the step 4, as that's where the drainage capacity of the geonet or the geocomposite start to being affected notably. Apart from those tests we just talked about, there are actually many other basic index tests, which includes the thickness of the material, the mass per unit areas, specific gravity, the carbon black, particularly in those PEs, the swell index, and the fluid loss for the bentonoids, and a lot more, which we don't have time to go through each one today. But you can actually go to the following link to get the whole basic index geosynthetic test that great R&D lab does, and our GAI-LAP laboratory, the GAI-LAP accredited list. Before we go to the specialized testing area, I just want to spend another 2 minutes talking about the sampling. For us in the testing industry, I think it's safe to say all of us agree that the proper sampling is perhaps the most important start to ensure that you can obtain some accurate test results. But I have to say, unfortunately, often it's ignored, particularly when it comes to the IQA tests sampled from the site. And we do actually have certain standards. For example, this GR standard GS16 just dedicated to how you can properly sample the specimens you want to send to the geosynthetic lab to do the testing without disturbing the specimen and affect the results. And most test standards also come with certain sections dedicated to the requirements on the sampling as well. So just to take an example for the GS16 standard here, it specifically asks do not sample the first 1 meter or the last 1 meter of the row, because that could be easily affected by the shipping, or do not sample material damaged by shipping and handling. And whenever possible, when you do the sampling, you want to have an assistance of a forklift to lift up those rows and cut it above the ground. And if that's not possible, at least conduct it on a flat, dry, and smooth surface. However, this is something we often have on the site. And you can imagine how this sort of sampling method can affect the performance of the products when it's arriving in the laboratory. Now that we have gone through the basic index test and the sampling, we will go through some interesting performance-based tests we do here in the GRAI laboratory. Why we need to do the performance test? First, the site conditions should be considered because these conditions can affect your geosynthetic material performance, make them very different from the values claimed on the TDS. And in those performance-based tests, we often do a suite of tests rather than a single test. And those test methods may be highly customized to suit the specific site conditions. And you are correct. Often the test program may take relatively longer compared to the basic index test to complete. And these test results may not be universal. That means they cannot be simply applied to another product or to another site condition, unfortunately. And very often we have a lot of conversations between the laboratory and the designer, contractor, and even the asset owner, because that helps us to plan, execute the test program accurately, and that's suitable to the site we are looking into. A few examples we do here, including the in-plane transmissivity test, the shear box test, the cushion protection test, the hydraulic conductivity test using the incompatible liquids, and a couple of durability tests investigating the GCL downslope erosion, the pod immersion test on the geomembrane or geotextile durability, and the outdoor exposure test, particularly focusing on the UV endurance. So we will go through each one in a little bit more details in the following part. First, let's talk about the in-plane transmissivity test. So this is kind of characteristics of the geonets or the geocomposites about their water discharge capability. And they can actually affected by the following side test factors, including the vertical load. So the higher the load, you probably expect like a lower drainage capacity, or as those geonets actually compress under the load. And also the boundary conditions that depend on your layer verification. It can be soft or rigid. That means whether you have intrusion of your geotextile or the adjacent layer into the geonet and impede the flow. Then the hydraulic gradient, which affected by your slope design or your drainage capacity problem, and also the loading time, because the longer you test, the creeping effect of the geonet may further decrease the drainage capacity compared to a shorter compression test. So this is the equipment we use here at the grade. We call the transmissivity flow box. And this is a simpler diagram I got from the test method ASTM D4716, which is the test method we follow here at the grade. When we test those ones, we always ask the client about the four parameter or the conditions that should be customized to reflect the actual project specific conditions. And sometimes we'll also suggest the client, instead of doing a 15 minutes seating load, which we call the quick test, 100-hour seating should be preferred because that can be more representative to the long-term drainage capacity under the pressure for the geonets or the geocomposites. And in GCA8, it actually gives some general, influence of such conditions on the transmissivity or the flow rates. As you could see here, as the gradient increase, you generally have a higher flow rate. However, I must note the transmissivity may actually get smaller because the presence of the turbulent flow. And in terms of the normal strength, the normal compressive stress, you could see here as it goes higher, you would expect like a slower flow rate because the compression of the geonet and further impede its flow. The next one we want to go into is a shear box. This is a very frequently requested test here at the grade. This is because that slope stability is one of the most critical design concerns when it comes to the geosynthetic material, particularly when you are using them in a composite liner system. On a slope in, say, for example, a waste container like landfills or like a mine site. This can include both the interface between the geosynthetic and the soil, or just the internal and the interface shear of the GCL. And you can see here, they actually follow different test standards, which means the details of the tests are slightly different from each other. And we use our specially designed geosynthetic large-scale 300mm shear box to carry out those tests. And a couple of factors I want to bring up here that we need to consider when we request a test. First is the normal stress range. This essentially needs to be reflected to the true site condition as a nonlinear nature of the failure envelope in shear resistance Moore column failure analysis. And the second one is the saturation conditions and the displacement rate, as these two eventually decide how your pore pressure develop or dissipate in the shear test, whether you would have the clay softening or the lubrication effects on the interface. And also, we came up the temperature control as well, because some of the material, they are actually pretty sensitive to the elevated temperature, which we could encounter in the case of landfills because of the biodegradation, or some mine sites because of the chemical reactions. And at GRADE, in the last 10 to 15 years, we have developed a large database on the interface or internal shear test on the on a variety of products we supplied or manufactured in a large normal stress range that between 10 to 500 kilopascal. We also have the interface shear between the geotextile, different material like geomembrane, GCL geomembrane, and geotextile to concrete even. And we also have many database for the GCL internal shear resistance and also for the geocomposites. Here are just a quick example of the current database. This year we tested on certain products we have here. And if you happen to have certain questions regarding to our products, you are more than welcome to contact us, and we can dig into our history of the database and see if something we can help. And if it's something like we don't have at the moment, we are more than happy to help you test them. And last about the shear box, I want to talk about the temperature control. As mentioned in the last slide, in landfill and mining applications, the liners can be influenced by the elevated temperature, and the products may behave quite differently under those high temperature conditions. For example, like the softening of the bitumen in BGM or the bentonite dehydration in GCL. Therefore, at GRADE, we have modified the shear box to enable it to test with the elevated temperature. For example, here, using an immersed condition like a hot water circulation. And we also developed recently to test the elevated temperature in a dry condition using the hot plates and thermocouples. The third test I want to introduce for our GRADE laboratory is the cushion protection test. So this test have become very popular because people really want to understand when geomembrane used in the applications such as landfills, they tend to have the strain-induced stress cracking from the overlying aggregates due to the normal stress. And in these cases, geotextiles are often used as a cushion layer to protect the geomembrane. However, their protection efficiency needs to be quantitatively evaluated. And hence, we use a modified ASTM D5514 using the site-specific aggregates pressures and subgrades to carry out such assessment. And these are the cushion protection equipment we use in the laboratory. And we use these thin aluminum detection sheet to actually record the strain that happened on the geomembrane due to the intrusion of the aggregates. And then we send it off for the 3D laser scan, and then we can calculate the strain based on the deformation ratings from the laser scanning results. Again, a couple of factors we need to consider here when requesting the test. First, whether we should include the subgrade. So the traditional cushion protection test actually does not include the subgrade. It only includes the geotextile, the drainage aggregates, and then the geomembrane and the detection sheet. However, what GRADE has found in the last 10 years of testing is that the subgrade can actually provide a bit support to the tested geomembrane and the geotextile. which counteract the intrusion of the aggregates. And to be fair, it's more representative to what actually happened on the real side. So we did a bit of comparison study, and this is a quick comparison here. So under the same confining pressure, using the same aggregates and textiles, we actually find with the inclusion of the subgrades, the harder the subgrade are, the smaller cumulative, the smaller maximum strain you could observe from the geomembrane. Therefore, it is regarded as more realistic and less over-conservative to include the subgrade. The factor two is your aggregate type, particularly the particle size and the angularity, because they are the two factors that eventually control how aggressive they are. The wind shapes are different. Notably, please note that even aggregates with similar or identical PSD, they can actually generate very different results because they are very different in terms of the how aggressive they are. So the four pictures here are just a few examples of those different shapes, size of the aggregates we receive at grade to carry out those tests. And all of them are the site specific, which means they will be using the same aggregates on the site as we tested here. And the table here basically shows when using the same cushion geotextile under the same pressure, when your aggregate size decrease, you would have like a huge drop down of the maximum strain detected. However, selecting the size of the aggregates is a balance here because you don't want to go too fine because that could affect your drainage capability. But all in all, we do suggest every time when you request such tests, the site-specific aggregates are the keys to provide the accurate numbers. The third factor, though, is the geotextile type. We do see in some of the specifications from the designers, they nominate the certain mass and thickness as a control factor for the cushion, the protection geotextile. While they are the control factor, they are not the only ones. Other factors, for example, what the raw material those geotextiles are made of or how they are made of, are also factors can affect the geotextile performance in terms of their cushion protection behavior. So an example here, these are the tests done at grade using all different sorts of the geotextile manufacturing from polyester, polypropylene, and using either continuous filaments type or the staple fiber type. And we tested them under using the same aggregates under the same pressure, and we obtain such a tendency of the max strain obtained from those different geotextiles. And what we discovered is that when the sample mass of the specimens are the same, the continuous filament, which polyester, which is a blue dot here, actually outperforms the other geotextiles compared to it. Therefore, apart from the mass and thickness, we do recommend people pay attention on the raw material and how they are manufactured, and as these can affect the performance as well. Next test we want to dive into is the hydraulic conductivity. So this is quite important for the GCLs as they are essentially a hydraulic barrier system. So we at grade, we use the ASTM D6766 and relevant methods that modify from it to investigate how our GCL products to perform when exposed to the aggressive chemical environment. So these are the equipment we use. And the two small cells on the side are the toxic chambers because they have to be used when we test the incompatible liquids to separate the contaminated and sometimes corrosive leachate from the triaxial control panel. And this is like a general diagram of how these tests are going to be tested. Hydraulic conductivity of GCL, again, can be affected by a few factors. For example, the chemical environment, like the leachate or the subsoil the GCL is exposed to, and the way of the installation, whether they have the prehydration or without the prehydration. And regarding to that, we recently did a sort of research program, and we challenged our GCL with different prehydration conditions before they are exposed to a real landfill leachate. So you could see from the very poorly prehydrated condition to a very well hydrated condition. Fortunately, our GCL performs quite consistently along the prehydrated moisture content variations, which is a good news for us. But just that you need to mention, these results may not be true in other cases when the leachate is different or the GCL product is different. And also, the effective confining stress applied on the GCL may also affect that, which we also tested in the laboratory to validate that. As you could see, as your main effective stress increase, you actually experience like a decreasing of the GCL hydraulic conductivity. This is because at the higher pressure, the bentonite clay eventually consolidates and the pore volume actually decreases. The lower the void ratio, the less permeable it is. So that's come from the soil mechanics. And it's glad to see now, it's very common that clients ask for their GCLs to be tested with the site-specific leachate to determine their actual performance. Because in some cases, you find the actual values you got can be quite different from the values claimed from the manufacturer's TDS. And then we will go to some durability tests. Include the first one we will talk is the downslope erosion test. This is when the GCL and the GMB composite liner is exposed to the outer environment. And during the daytime, the evaporated vapor will accumulate on the area where GMB forms wrinkle, while at night it starts to form drips and drip down. And those DI water drips will initiate the cation exchange, and bentonite eventually can lose swelling and the erosion can happen. So this is a photo from the H et al. 2014. As you could see, the highlighted area here is where bentonite is eroded, and you could imagine here you essentially lose the hydraulic barrier performance for your GCL. So the Geofabrics really look into the performance of our GCL regarding to this. So we carry out the same test in a yearly evaluation fashion as per the H et al. 2014 methodology here. And what we found is like the pH plus variant axial has a very nice resilient performance to the downslope erosion. And using a daily wet dry cycle with 8 hours stripping plus 16 hours of air drying, the X2000 pH plus EcoSeal GCL does not show sign of erosion up to 55 cycles tested, and the current test is still ongoing. So we would like to see how it can perform with even longer testing cycles. Another durability test we often do is a pot immersion test under elevated temperatures. So by doing so, we can first expose the geosynthetic material that are interested to the site-specific chemical environment. And by increase the temperature, we can accelerate the degradation so we can analyze their, like long-term durability or the longevity. And these tests often takes longer than 90 days to complete. But as Carol pointed out recently, these immersion tests are really the key to determine the geosynthetic material such as GMB surface life in aggressive chemical environments. And similar test methods can actually be found in the international testing standards, such as those three listed here, with very different focus on the hydrolysis, the landfill leachate, and the acid alkaline liquid. And the grade can do all of them here if requested. An example here is just showing, the hydrolysis resistance we carried out on our bitumen G polyester geotextile following the test method 12447. In this case, we basically immerse our bitumen geotextiles into the DI water at 80 degrees C for up to 150 days. And on each testing durations here, we just pick up 10 specimens and test their strip tensile strength just to see how much degradation we have, and plot the strength degradation curve against the immersion days. And based on the test standards interpretation methods here, that test results verify that our bitumen A24G actually qualifies for 100-year durability in a pH between 4 to 9 and temperature not higher than 25 degrees C environment. And here in Australia, another often requested or asked question is your product durable when exposed outside due to different kind of reasons? This is because the very harsh UV environment we have in Australia. While we do have those accelerated UV tests, such as D4355 or D7238, it is very often not straightforward to correlate the accelerated UV results to the real life. Therefore, we do conduct outdoor exposure tests as per the ASTM test method D5970 to quantitatively analyze the material degradation when exposed to the real-life outdoor condition. And this is the UV exposure rate we have here just outside the laboratory. And once achieving the exposure time, for example, like 3 months, 6 months, a year, we will take off the sample and cut the specimens and test them using D5035 and to see the tensile strength degradation, using that as an indication of how the degradation happened. And we have carried out these outdoor exposure tests on our geotextiles at different locations across Australia, because this is a very wide country. We have very different UV index along the different altitude. And we do have the locations in Gold Coast here, and we also have Adelaide branch and Perth branch help us to do those UV exposure tests as well. And on the right-hand side is an example that we did last year on our different grades of the beaten products and how they perform when exposed to a 1-year outdoor UV exposure here at Gold Coast. And these data collected are really representative to different regions here in Australia and reflect how the geotextile performs when exposed to the real-life weather and UV conditions. Because in some cases, the client might want to expose their geotextiles on the site for a couple of months. And when they come to us, just to say, do you think that's doable? Or, like your geotextile can endure that sort of outdoor exposure? We would have the first-hand test results to let them know what kind of the strength they would expect after they expose outdoor for a certain period of time. And one last thing I want to bring to the test part is the polymer dosing in the rapid dewatering test in GeoTube. For this one, the GeoTube is a very safe and effective, easy dewatering solution that we work together with Solmax. And 3 stages are often included here, including filling the GeoTubes with sludge and then starting the dewatering process, and finally have the water solid separated, which is a consolidation stage. However, in some cases, the polymers such as flocculants or coagulants are required to actually enhance the whole efficiency of the process. This is an example that we sometimes get those slurries with very fine solid particles. So if you simply do it without the polymer help, what happens is those fines actually pass the GeoTube woven geotextiles, and you can't actually really separate the two. However, once a small amount of the polymer added, in this case is the flocculant, it helps to combine those fine particles together to form larger particles that can be retained on the GeoTube woven geotextiles, and hence help increase the whole process efficiency here. So this is something the GAI-LAP can help as well. So if you need anything, please contact us. We will let you know how can we proceed that. And finally, I'll just spend maybe 1 or 2 minutes of our R&D capability and some side trial experiments we currently are working on. So the GRI laboratory is a critical or the important role of our laboratory is to keep the innovation and evolution of the products to cope with more challenging geo-environmental problems. And therefore, in the R&D program, not just the basic index tests, but also performance-based tests will be carried out. And the aim will include revealing the mechanism behind the observed characteristics of the products and investigate the possibility of improving that. And the laboratory testing programs are developed to challenge the products that they will actually face in the real site. And this is the circle we do. We have the observations, then we raise the questions and bring up the hypothesis, and maybe also make the predictions of the performance of products. Then we carry out the actual experiments, and we will have more observations and repeat the circle until we know the very factor of the products that we developed inside and out, so we can make sure they perform as designed on the site. And another reason we do so is very often the client may come up with some questions we don't have the answer straight away. This could be due to the special site conditions, the unexpected product performances, which sometimes happen, and applications of a product that haven't been validated before. So to provide such solutions, it's not possible to just answer that through a simple test program. And therefore, we can actually work very closely with the clients to develop a very comprehensive investigation plan to adopt the specific conditions of the scenarios. This can involve the following procedure, like the literature research. Then we can propose the suitable products, and then we develop the test method to validate their performance. Then that may also involve some manufacturing specialized testing equipment or modifying the current one we have. And many of the cases that will involve some long-term tests. And we are proud to say we collaborate with some of the leaders in the industry and to provide more knowledges in the geo-environmental and the geosynthetic industry as a whole, not only as a company here. And while we are a laboratory, we are proud to say we also do some site trial experiments as well, because we believe that a full-scale site trial is possibly the most convincing way to validate the performance of a product by letting it experience in the real site exposure. While we know it is really cost, labor, and time-consuming, but we believe the importance of doing so. Therefore, at the Warwick, Queensland, currently the GAI-LAP is carrying out 2 site trials on a recent GCL product we are developing by installing them on both the flat ground and the slope. And we bury the sensors beneath them and keep monitoring their moisture temperature change to just see the barrier performance of the GCLs when fully exposed to the environments. And we would also periodically go to the site, collect samples, and do all these tests we discussed previously in this webinar to challenge their performance. So that's basically is today's webinar. To wrap it up, first we have to say testing provides us critical information about geosynthetic materials that is essential to a safe and efficient design. So it's really important to do the testing and to know the material you're using on the project. And the GAI laboratory is probably somewhere you can that can help you, because we have more than 50 ASTM and ISO standardized test methods that are actually GAI-LAP accredited to guarantee the accuracy of the test results. And we are also specialized at performance-based tests that incorporate the site-specific conditions to challenge the geosynthetic materials that they will experience on the site to give you more assurance on the geosynthetic performance. And we are proud to say we are a core unit playing a critical role in the product development in the Geofabrics. And therefore, we are open to external collaborations for research and development projects to explore the cutting edge of the geosynthetic and geoenvironmental industry. So if you find any useful information from this webinar, or you need a bit more information, you are more than welcome to contact us. You can find our contact information in the Geofabrics website. And we are happy to we are looking forward to see your feedbacks on that. So that's basically today's webinar. So thanks for joining us. Now we have about 10 minutes Q&A questions. So if you have any questions, sorry, I forgot mentioning that. So you could actually type in the Q&A box. And when I see that, I will answer one by one. So if you have any questions, please raise, and I'll try my best to answer. Okay, it seems pretty good. No questions so far. Seems it's a very, I mean, it's a very straightforward and not very technical detailed presentation. But like I said, if you are interested in any of the more detailed information regarding a certain test method, okay. So we got a question here. So Shahar just asked, is GAI-LAP a NATA certified lab? So the answer to that is no, we are not NATA certified because NATA essentially requests for like an independent third-party laboratory, and we are not. But as I mentioned, we are a GAI-LAP accredited one, and the GAI-LAP actually guarantee a very high accuracy because mentioned previously, like every year we need to do these proficiency tester program on all the test methods we are accredited for, and the results will be compared between more than 100 laboratories like worldwide. And then the GAI-LAP would actually notify us whether you have done all the tests correctly or if there is any issues in a certain test method that you need to look into. So it's actually a pretty controlled like laboratory environment. As mentioned, the GAI-LAP program is essentially framed around 17025. So same as NATA certified, but it's just like we are not like a third-party laboratory. And Vinod just asked, so wetting and drying, how these affect the performance? I'm not sure like what material you are talking about. So if it's a GCL, it really depends. So in our case, we have done the GCL, one of our products, we have done the GCL wet dry circle, and currently it's reaching to almost 100 wet dry circles. And we then challenge it, like using the actual liquid they are going to expose to, which is in this case the rainwater. And the permeability actually doesn't degrade much in after like 100 circles. So, however, my previous experience, if you have a much more like aggressive like liquids, then the wet dry circles may become an issue because the chemical environment or the elevated chemical condition may like suppress the bentonite self-healing performance, and you will find the fractures or the desiccation cracks you generate during the wet dry circle may not heal once it's re-wetted, and such behaviors may be like be enlarged as you endurance a longer and longer wet dry circle. So yeah, that's really depends. But for some other material like the geomembrane stuff, we're probably less sensitive to that. But again, it really depends on the condition, whether you have those aggressive, chemical environments, or at the same time, you probably also have some elevated temperature. So can be quite site specific. I reckon in certain cases, it's better to carry out some actual tests to validate that to be suitable to your specific site conditions. Right. So Simon just asked a question. So just curious, how you separate the sample in a large direct shear box sinks. So a couple of ways to do so. At the moment, some designers request the samples being separated like separately outside of the shear box and then installed on the shear box. So this is there are certain ways of doing so, but you will need to control the confining pressure, but also like on the bentonite loss on the edge, how to control that. So that's an important topic. And you may also be able to separate your sample in the shear box, in the shear box itself. However, we did have a comparison between the two separation methods because in the shear box, so you would, particularly when you're testing the GCL as a single material, you would have those gripping plates on the top and the bottom of it. And those gripping plates, although they are perforated, they don't have as good as like permeability such as porous disc. So you may have a little bit less saturation, fully saturated condition compared to those ones actually saturated outside by immersed fully in the water. So Yeah, so this is the way we do so. But yes, our current equipment does have a limitation, is that the water level cannot go to the very top of the box, which means your top half box, like maybe 2/3 of it, cannot be fully immersed in the water. So that makes, for example, if you want to test the soil direct shear or the aggregates direct shear, particularly in a consolidated drain condition, our equipment might not be the most suitable ones. So hope that answers your question. And meanwhile, seems like we don't have more questions. And if that's the case, thank you very much. Thank you guys again to spend your time, valuable time to joining us for this Geofabrics Academy webinar. Hopefully you will grab some useful information from this presentation. I believe this one will be a recorded version, so later probably the recorded video will be sent to you as well. And if you need any further information, feel free to contact us. Again, thank you very much. We will see you another time.